This page is going to look an awful lot like the previous one, but that's because we're looking at a similar reversible inhibitor. In this case, however, we're talking about a non-competitive reversible inhibitor. And as you can imagine, what we're going to do is start as we did down here with the characteristics. I made the same mistake on this page. We need to say not substrate, but rather inhibitor does not bind in the active site. Remember, the defining feature of a competitive inhibitor was that it bound in the active site. So let's go back to the Michaelis-Menten model and consider what would happen with a non-competitive inhibitor. What it means is that there is another site, another groove on the surface of the enzyme to which the inhibitor can bind. So, as before, we can have the enzyme inhibitor form a reversible complex E.I, or the enzyme inhibitor can form a substrate complex E.S. But in this case, because they are binding to different spots, we can have the substrate bind to the enzyme inhibitor complex to form a triple complex, E.S.I. Likewise, if the substrate binds first, we can have the inhibitor bind and reversibly form the same thing. So all of these things are possible. And what we can say is that the inhibitor doesn't affect substrate binding. So if it can't affect substrate binding, how does it inhibit production of product? Well, the answer is that once the inhibitor and the substrate are bound, the conversion to product is slowed down or maybe even ultimately stopped. So instead, the chemistry is slowed or stopped. So let's have you do what we did before. I'd like you to consider what would happen to the Vmax, what would happen to the Km. Up, down, or no change. Pause for a moment, see what you think. Okay, there were definitely some clues along the way. When we said that the inhibitor doesn't affect substrate binding, since Km is a reflection of substrate binding, we would expect that that would be unchanged in the presence of a non-competitive inhibitor. Now let's look at the other part over here. This part, which is all about the chemistry, is slowed down or stopped. And that is reflected, the chemistry of course, the catalysis, the reaction rate is reflected in the Vmax and Kcat. So in this case, the Vmax is going to be lower in the presence of an enzyme inhibitor that is a non-competitive in nature. Okay, great. Let's continue on in the same way we did before. Let's go down to our graphs. Let's look at our direct plot, VO as a function of substrate, and 1 over VO as a function of 1 over substrate. We have dashed lines that represent in the absence of any type of inhibitor in both cases. Let's pause and see if you can come up with the curves or the lines that represent in the presence of non-competitive inhibitor. See what you come up with. Okay, let's make a note that the Vmax is going to be lower in the presence of a non-competitive inhibitor. So we're going to level off at some place that is significantly lower than we saw before. This is tricky though, to try to draw this. Remember, this is the 1/2 Vmax, which would put our Km right about there. Since this is our new Vmax and it's a little bit lower, the 1/2 Vmax is going to be about right there, 1/2 of that, and we need it to be in the same spot. So let's grab that green pen and make a note that it should be right about there. It's not at the same spot where it was before. not the exact same spot, but it's the same spot on the y-axis. That's not a very good drawing. That's very difficult to draw that. Nonetheless, that's how you do it, and that's a reflection of a lowered Vmax and essentially the same Km. How is that going to look like in a Lineweaver-Burke plot? Well, once again, I want to give you a hint. It's going to be a straight line, and it's going to cross the other dashed line at a particular point. Which point is unchanged? Let's see if you can try that. Okay, I hope you note from above that the Km is unchanged. That means the x-intercept, which is -1 over Km, is going to be the same spot. Did you remember what I said on the previous page? If an inhibitor lowers velocity, it raises inverse velocity. That's a point where we always find people doing things wrong on exams. So we're going to have a straight line like that, representing in the presence of inhibitor, we see it rotate up. You have a same Km or same x-axis intercept, but we have a higher 1 over Vmax y-intercept. Remember, a higher 1 over Vmax should be a lower Vmax, as we see from over here. Very confusing. Nonetheless, that's how it works, and this is how we can use kinetic plots, whether direct Michaelis-Menten plots like we see over here, or indirect Lineweaver-Burke plots especially, to determine which type of an inhibitor we have. To finish off, lastly, I want to say, parallel to what we said on the previous page, because they don't bind in the same site, in the active site, substrate and inhibitor do not necessarily look alike. They might, but there's no reason that they should, because they don't have to complement into the same space. It's like saying, well, my hand goes in a glove and my foot goes in a shoe. They're different spaces. Why would a hand and a foot have to look alike? Okay, so let's leave it at that, and we'll finish off this entire chapter with one more discussion of looking at examples of these types of inhibitors.